Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's weekly contest, robot collisions. The problem is very interesting and we have very similar problem in one of the last bi-weekly contest 106 as well, wherein again we are given some robots, they were moving either left or right and there are some collisions involved and you have to determine some property after all the collisions are done. So if you haven't solved that particular problem yet, I would strongly encourage you to watch this video and solve that particular problem as well by yourself. I would link that video, this video as well as the problem in description below. Make sure to check it out. So let's move ahead with this particular problem. The problem states that you are given n1 indexed robots, each having a position on the line, health and a movement direction. Now you are given these three arrays: positions, health, directions. Position denote the position of the robot, health denote the health of the ith robot, and direction denote the direction of the ith robot. The direction can be either left or right, meaning that either the robot, like whether the robot is moving to the left or it is moving to the right. Now all the robots will start moving simultaneously at the same speed in the given direction. Now if two robots ever share the same position, they will collide. Now if two robots collide, the robot with lower health is removed and the health of the other robot is decreased by 1. Now if both of them have the same health, they both will be removed, right? So whichever, if one have greater health, the greater health will survive, the lower health will be removed. If they both have same health, both of them will be removed. Now our task is to determine the health of the robots that will survive the collisions in the same order that the robots were given. Right. So let's take an example. Let's say you have these five robots, R1, R2, R3, R4, R5, and the positions of these robots are given as 5, 4, 3, 2, 1. So basically it says that R1 is at position 5, R2 is at position 4, and so on and so forth. The health of these robots are given as 2, 17, 9, 15, and 10. So R1 has health 2, R2 has health 17, R3 has health 9, and so on and so forth. And the directions are R. So basically everyone is moving to the right. So because everyone is moving to the right, none of them will collide, and because none of them is colliding, the health will not change and hence the output will be exactly same as the input. Now notice that even though robot 5 comes first in the number line, we have to return the output in the same order as the input, right? So that's just one thing that you need to take care of. Let's take one more example. Let's say there are 4 robots, R1, R2, R3, R4. R1 and R3 are moving to the right, R2 and R4 are moving to the left, and these are their corresponding healths. Now what will happen after 1 second? R1 will be at 4, R2 will be at 4. It means they both are sharing the same position, that is they have a collision. Now because they have the same health, both of them will be removed, right? And at the same instant, that is at t equals to 1, this will also have moved one position and this will also have moved one position. So basically after t equals to 1, robot 3 is at 3, robot 4 is at 5. Now at t equals to 2 again, robot 3 and robot 4 will collide, and this time because robot 3 has greater health, robot 3 will survive the collision and robot 4 will be removed. Now there is only one robot which have survived all the collisions and the health of that robot is 14. Like initially it was 15, but because it is given that after collision you have to decrease the health of the other robot by 1, so we have to decrease its health by 1, and hence the health of robot 3 is 14, and hence 14 is the answer. Let's take one last example. R1 and R2, R3 and R4. R1, R2 has the same health, R3, R4 has the same health. You can see R3 and R4 will collide, and because they have the same health, they both will be removed. R1 and R2 will collide, they both have same health and they both will be removed. So finally none of the robot have survived all the collisions and hence the answer is empty. So hope the problem statement is clear. Now before actually diving into the solution, let's first try to disambiguate some of the things that is not given in the problem explicitly, right? So it is like in this kind of problem, it is always essential to disambiguate certain aspects early so that you don't end up solving a wrong problem. I have done that many times in the past, so I'm just I will suggest you to do that early on, so that you don't end up solving a wrong problem. So let's just think of some scenarios of collision. So basically there are two important things here. One is collisions and second is the health. So we just think of is there any disambiguity in terms of collision, and we'll also think of if there is any disambiguity in terms of health. So what about collisions? Let's talk about collisions first. So collisions, they have said that what to do if two robots collide, but they haven't mentioned anything about what to do when three robots or basically greater than two robots collide. So what will exactly happen in these scenarios? So will this scenario ever happen is the first problem. So this will never happen. Why? Because of these two constraints. All the positions are unique and they all are moving in the same speed, right? So let's talk about this scenario. R2 is moving to the right. R4 and R1 both are moving to the left. Now R4 will collide with R2 and R1 can also collide with R2, but because R4 and R1 are moving at the same speed, it is certain that R2 and R4 will be colliding first, and after collision one of them will survive, and that may collide with R1 as well, right? So because it is always true that before this R1 can collide with R2, R4 should already have that collision with R2, and because that's the case, there is no place where there are three robots possible at a given instant, and hence we don't need to worry about the scenarios where there are three greater than two robots colliding at the same time, right? Now one more thing that some of you might be thinking is if two robots ever share the same position, they will collide. So the definition of collision is they both share the same position. Now is the position needs to be a integral position? For example, let's say this is position 1, this is position 2, this is position 3. So R2 and R4 is colliding at position 2, so that is fine. But let's say this case where R2 and R4 is at position 1 and 2. So if they have to collide in non-integral position. So if this non-integral collision is something which is not allowed, R2 would have moved to 2 and R4 would have moved to 1 without any collision, right? So this is not explicitly cleared in the problem statement, but in the third sample they have made it clear. Basically R1 and R2 is at 1 and 2 respectively, and they both are colliding. So basically this is also allowed, right? Now similar to collisions, there are some ambiguity in terms of health as well, right? I would encourage you to pause the video and try to think of scenarios which are ambiguous in the problem and see if you can disambiguate it. So one such scenario is we have been told that we have to reduce the health of the robot which survives the collision, right? So let's say a robot has health 1 and it survives the collision. So you have to decrease its health by 1. So basically the health of this robot will be 0. Now will this robot continue further, or this is completely removed, right? So the answer to that is this particular constraint. So the constraint says that the health will always be greater than or equals to 1. So this robot R2 will be colliding with a robot which have a health greater than or equals to 1, right? Because that's what given in the constraint. So because that's the case, either it will be colliding with a robot of health 1 or it will be colliding with a robot of health greater than 1. In case it collides with a robot of health greater than 1, this will be removed, so there is no point of this health reduction at all. In case it collides with a robot of health 1, both R2 and that particular robot will be removed. So again there is no case of having a robot with health 0. So basically because of this constraint, there will never be a scenario where a robot with health 1 wins the collision, and because that's the case, we'll never have a robot with health 0 after a collision, right? So hope these all ambiguities are clear. Now once we have removed some of the ambiguities, let's now try to solve the problem. If you haven't thought of brute force solutions yet, I would strongly encourage you to pause the video right away and try to at least come up with a brute force solution by yourself. So the brute force solution is very straightforward. We will do exactly what is given in the problem. So let's say there are 4 robots, R1, R2, R3, R4. R2 is moving right, R4 is moving left, R1 and R3 are moving left and right respectively. And these are the healths of the robots. So R1 has health 8, R2 has health 7, and R3 and R4 has health 9 and 6 respectively. So now what, like, we need to find out the result in this particular scenario. So what you will do, you will just simply simulate whatever is given in the problem. So let's say you will say, okay, I will try to find out what happens after time t equals to 1. So at time t equals to 1, what will happen? This will move here, this will move to the right, this will move here, and this will move here. So basically R2 and R4 will collide at position 2, or whatever this position is, and because R2 has greater health than R4, R2 will survive the collision and R4 will be removed. So basically we'll have R2 will keep moving right, and the health of R2 will be reduced to 6, right? Now what happens after that? Let's say t equals to 2. Again same thing, R2 will move to this to right, R1 will move to the left, and R3 will continue moving to the right. So R3 will be at some position, R1 comes here and R2 comes here. So again, what happens at t equals to 3, or in between 2 and 3? These two will collide somewhere here, right? And because of collision, one of them will survive because R1 and R2 doesn't have same health. So R1 has greater health, so R1 will survive, and because R1 was moving left, so this will be the new state, right? Now finally you can see R1 is moving to the left, R3 is moving to the right, so they can't collide ever, and this is the final state. There is no more collision required, and because there is no more collision, health will not change anymore, and this is the final health. So basically R2 and R4 are completely removed, and the final health is 8 and 9, or basically 7 and 9, because this will also be decreased by 1 after a collision. So 7 and 9 is the final answer. Now what is the time complexity of this entire solution? What is the time complexity to make this switch, like to just make sure what happens after t equals to 1? What is the time complexity of this particular transition? The time complexity is simply order n, or order r, basically number of robots. Why? Because what we are doing is we are just updating the position of the robots, and while updating we can simply figure out whether there is collision involved or not. If there is a collision involved, so there are two scenarios, whether where 2 robots are at same position or 2 robots were at adjacent position. So whenever a collision is involved, we can simply go to the health array, figure out who will survive, and update the health as well. So basically this entire thing can be done in order r time. Now how many times you have to do this is the question. So again, encourage you to pause the video and try to think of this particular thing by yourself. So what can happen in the worst case? In worst case, this R2 will collide with R3, right? Basically you have to keep on doing this until there is no more collision, right? So as we have already discussed that after a collision, either one will survive or both of them will be removed, right? So in best case or in worst case, what can happen is R2 will be colliding with R3. So basically the first and the last one will be colliding. So because they are colliding, it means whatever was there in between would already have collided, and none of them will survive, right? So how many, like after how much time this R2 and R3 will collide will give us how many transitions we have to do. So let's say R2 is at position 0 and R3 is at position t. So they will both collide roughly at position like roughly after t by 2 time, right? So here this value of t is 10 to the power 9, right? So because that's the case, we will be doing t number of transition where t is up to 10 to the power 9. So total complexity is order r into t, right? So you might have already figured out that this will not pass because t itself is of the order 10 to the power 9. So you have to reduce it. Now how exactly will we reduce this? Basically how we have to remove this factor of t for sure, because t is itself 10 to the power 9, so we have to remove this factor of t. Now where from this t was coming from? T was coming from the fact that we were doing the transitions one by one, right? And because of this we have to incorporate this t number, like t number of transitions. So can we reduce this? And if we can, the complexity can be reduced as well. So that's what the target would be. Now before jumping ahead, let's just think of what will be the final state, or what are the possible final states. So as we have discussed already that collisions can only change the health. So final state would be the state wherein there is no more collisions possible, right? Now if there is no more collision possible, it means all the robots are moving to the left, right? Or all the robots which are remaining are moving to the right, right? Or some robots are moving to the left and then some robots are moving to the right. So either of these three possibilities is a final stable state. Because everyone is moving at the same speed, none of them will collide and none of these will collide, and these all will never collide because some are moving to the left, right, and some are moving to the right. So left and right will never collide, and among right they will never collide because they all are moving in the same speed, right? So these are the three final states which we want to be at. Now previously what we were doing was we were figuring out we were just incrementing time one by one, and as a result of that increment we encountered some collisions and we resolved those collisions as well. So now instead of incrementing time one by one, we can simply go ahead and figure out when is the first collision possible. So instead of saying that okay, just do the iterations one by one, and then whenever collision happen you will just update the health. You will say okay, I know that R2 and R4 will be colliding first, so I will simply remove one of them, and I don't care about time because the problem doesn't ask me at what time the state will be stable. The problem just asks me that what will be the final health. So I don't care about time at all. I will simply do the collision and update the health of the corresponding parties. So in this particular scenario, so let's just say that you have a string L and R which are the position of the robot, and there are some else before. So this else is valid because you know that a string of L or a stream of L is a stable state. Now let's say you have some R's after that. So again these R's are also valid because you know that L and R is again a stable state. Now the problem arises when there is some L now, right? So if there is some L, then you know that this R and this L will be the first one to collide for sure, right? Now because they are colliding, what would be the result? The result could be either both of them are removed, right? So basically there is nothing, or either left one will survive the collision or either right one will survive the collision, right? So these are the three possible results. Now in the first scenario where none of them survives, so in this case both L and R are removed, so the final string is this, and this string is a stable string. So basically you have converted an unstable string into a stable string by just performing the collision, right? So that is fine. Now let's say L survives, right? So in this case R is removed. So because this R is removed and L is survived, you will again have a non-stable string. So you know that this L and this R would be the second one to collide, right? So you will simply, like what we get right now is just what we have got previously. So we can simply perform the collision and move forward. Now the last thing is we know that R survived. So basically L lost the collision and R survived. So in this case again we have a valid string. So basically what we are saying is, in each of these scenarios we will have a valid string at the end. So what will happen is, after you have processed this L completely, you will be getting one of these two strings. Either this L will collide with this R and win, so this R will be removed, and then this L will collide with this R and again win, so this R will be removed, and similarly this L will collide with this R, again win, this R will be removed, and so on and so forth. So basically finally you will have something like this, which is a valid string or a stable string. Or you will say that this L collides with some of this R and won, but it also loses with some of this R. So in that case the string would be this. So in both the scenarios you will be ending up with a valid string. So basically what we just saw is, we know these are the three possible type of valid string or a stable state string. We will simply keep on performing the operations and we will be reaching at a point whenever there is an invalid character appears, we will just perform the collisions, and after collision we are sure that we will be ending up with a valid string again, right? So hope this entire thing makes sense. So what is the time complexity of this entire thing? What we are doing, we are processing each robot one by one from left to right, and whenever there is a robot which doesn't conform to the valid string or a stable state, we will perform its collision with the previous robot. Now this collision can go all the way up to last one, right? So for a single robot can collide with all the robots, right? And this after the collision we'll know that one of these two states will be reached. So basically for each robot we are require almost order R time to finish, and there are R number of robots, so you can think that the complexity is order R square. But this is not completely true, because once this robot collides with some other robot, that robot will be removed. Either that or the current one is removed. Basically at every state one of the robots is getting removed, and how many robots you can remove at the end? Only R, right? So the overall amortized complexity is still order R, right? Again, just to reiterate the part, we are performing the operations from left to right, or we are processing the robots from left to right, and as soon as we see that there is a non-conformant state, we will simply collide with the previous robot and make sure the state is conformant. Now this collision will remove one of the robots, and because over the entire lifetime we have only R robots, so only R collision can happen at max. So overall complexity is order R. So let's look at one final example that will make this entire thing much more clear. Let's say these are the 5 robots and these are their healths and these are the positions. So I already sorted the positions in left to right, so that it is not hard to dry run over this, but in the given problem they are given that positions may not be sorted. So in that case you have to keep this tuple and keep on sorting based on this tuple. Now we have this RRR. So again we got first R. So R is a valid string, so that's fine. We got this R. So let's just note this position as well. We got another R, that is again fine. Let's note its position as well. Now we got another R, so that is also fine. Let's note its position as well. and now we got an L. So as soon as we got L, this is not a valid string. LR is valid, but RL is not, right? So we know there will be a collision. So basically these two will be colliding. Now what will happen after collision? So let's see, this R was, sorry, this is 2, right? So this R was the R of position 2, right? So this position 2 is colliding with position 3. They both have same health. So because they both have same health, both of them will be removed. So basically this will be removed and this will be removed, and finally this will also be removed because your current state will be now this, right? Now we will say, okay, let's move forward, let's process another one, which is R, which is L again. So again, you know this is not valid, so you will say, okay, I will start doing the collisions. So you will say, I will collide this L with this R, and this R was position 1. So you will say, I will have a collision between position 1 and 4. Now position 4 clearly has larger health, right? Or robot 4 has larger health. Because it has larger health, this will survive the collision, and hence this will be removed, right? And the health of this one will be 16 now, right? So this is now removed, right? So let's just clear this up. Now again these two will be colliding, right? So what was this R? This R will be the R of the 0th position. So again this 0 and 4 will collide, 16 and 15 will collide. So clearly robot 0 has smaller health, so this will again be removed, right? So this will be removed. So finally you will left with just one L. So this is also removed, right? So you will just left with one L, and you will also update its health to 15 because there is just one more collision possible. So this L is a stable state now, and there is no more robots to be processed, and hence we reached a stable state. We can simply iterate over this array and figure out which all robots are active and what are their health. So in this particular case, only 15 is only robot 4 is active, and the health of the robot 4 is 15. So we'll return 15 as an answer, right? So hope this entire solution now makes sense. Basically what we are doing, we are simply iterating over the robots one by one and figuring out what is like, instead of waiting for the time to collision, we are simply colliding them right there itself, because we don't need to worry about what is the final time after which we will attain the stable state, though it is possible to find that time as well, but for now we don't need that time, and hence we can simply do the collision and bring the current state to one of the stable states where there is no more collision possible. And we saw that to bring this to a stable state, it is always possible to bring a non-stable state to stable state by just performing the collisions. So this will either be translated to this or to this, and both of them are stable states, right? So overall complexity is still order R, because it depends on number of collisions that happen, because after every collision we are removing at least one of the robots. So in worst case we will remove every robot, so there will be at max R collisions possible, and hence the complexity is order R. So hope this entire solution makes sense. You can implement this solution very easily by just maintaining this data structure, which will give you the where you will store the list of all the R's, because that's what matter at the end. So you can use a stack or a queue or a simple vector as well. So all of them will work here. Stack is much more intuitive here, because what we are doing from here is we are always looking at the top one, or basically the last R, and based on that we are deciding whether this L will be removed or this R will be removed, or both of them will be removed, right? So you can use stack here, but as I mentioned, you can use queue or vector as well as you want. So I would strongly encourage you to pause right away and try to code this entire solution by yourself, because again, as always, if you don't code the solution by yourself, you will not be able to retain this particular concept for a long number of time. So next we're looking at the code. The code is straightforward, as we have discussed. We'll first sort the robots by their positions. So we just have a struct here, and the comparator just looks at the position and sort by positions. So we just sort the robot by positions. After that, we maintain a stack of write. So basically we just need to take care of all the writes at once, because these are the ones that can be an issue whenever there is an L after it, right? So we maintain a stack for all the writes. If the robot is moving right, we just push it to the stack and continue, right? If it is not moving right, it means it's moving to the left. So if it is moving to the left and it is the first one that is moving to the left, or basically there is no right at all before me, it means the left can still be allowed, right? So basically if there is no right at all, you can have robots that are moving to the left, because a stream of L is a valid stream. So that's what we have done. We have if the direction is not R, it means direction is L. So we just check if there is no R at all. If there is no R at all, this robot can still move and will just continue. But if there is at least one R, it means there will be collisions, right? And because there will be collisions, we have to make sure that we have corrected the state to a stable state. So what we will do, we will simply look at the position of this L, look at the position of this R, figure out their healths and compare their healths, and one of them will survive or both of them will be removed. So that's what we have done. We have figured out the last robot, which will be colliding with the current one. If that robot health is greater than the current health, it means the current robot will not survive. So we just subtracted the health of the last robot, and we also updated the health array. So that is initial array that is given to the problem, because this is what we will be using at the end. So we just updated the health array with the correct health, and we updated the health of the lth robot to 0, because that robot is now removed. And finally we push this to the stack again, because this is still alive. This survived the collision, so this is still alive, so we just push it to the right array. If that's not the case, it means L will win the collision. So L will survive the collision. So in that case, the health of R will be 0 and the health of L will be reduced by 1 and will continue. So because we are keeping on doing this until there is at least one L, it will collide with, or it will try to do a collision with all the R's possible. So with this continue, we'll collide with the next, we'll look at the next R. If both of them are equal, like if both of them no satisfied, means the health of both L and R are equal, in that case you will simply remove both L and R, and because you already have removed R from the stack, you don't need to do anything else. You will just simply break out from the loop, because there is no more collision possible. Previously, before the introduction of this particular robot, everything was stable. So after this robot is removed completely, everything will remain stable, right? So you can just simply break out. And finally, we'll go over all the robots, and because we have updated the healths to 0 for which didn't survive the collision, so we simply check whichever has health greater than 0, we'll simply push those to the result and return that as an answer. So hope this entire solution makes sense. And as we have discussed initially, I would encourage you to solve the biweekly contest 106 problem as well. That is also somewhat similar to the current problem, and that will also help you get some insights on how to solve similar kind of problems given the different kind of constraints. So hope you like the video. If you enjoy, give it a thumbs up and do subscribe if you haven't already, and I will see you in the next one. Thank you.